Okay, what's below represent non-real zeros. Let's start with real zeros. I've got a version of this curve in blue, and let's say I just scooch it down a little bit. If this curve were in the blue position, I hope you recognize that this thing is 1, 2, it has 3 zeros, therefore it's probably third degree. Seems like it has a negative leading coefficient. So the fact that it's third degree means it should have three zeros. If you move it up, right, just by changing the number that's added to it on the end to vertically translate it, it doesn't do anything to the degree, and so it shouldn't do anything, but it can change what kind of zeros. In this position, this curve has 3 real. Bring it down a bit. Now I would have a real 0 right here, and then a 0 of multiplicity 2 right here, so the total is still 3. And if I come down another fraction, there, 3 zeros. But now one of them is real, and this multiplicity 2 that was happening a moment ago no longer represents real zeros. It doesn't make contact with the x-axis. In this case, we say that there are still zeros here, and there are still 2 of them real. So for this first question, this position, 1 real root, and then 2 non-real roots. Now it's a 1 and a 2. Now it's 1 and another pair, multiplicity 2. Now it's 3 real roots, and everything's fine. If we come up, I'm going to line it up now. Here again, we get a case where we have 1 real root, and then a root of multiplicity 2. And then if we come up just a bit further, what happens? We've a real root right here where it actually makes contact with the x-axis. And here, remember how we had 2 real roots when this thing was just a little lower? There are still 2 real roots, and they are in this region. It's just that they aren't real anymore. They're now complex, or sometimes we call them imaginary or non-real. So this curve should have 1 real and 2, I prefer the term complex, so I'm going to go with that. Complex, imaginary, and non-real mean the same thing in this context. Notice the total is still 3, which supports that this thing is a cubic, which we've been saying all along. Okay, so the process for these is take your curve, imagine moving it up or down until you get the maximum possible number of real roots. That's how you're going to figure out the degree. And then from the degree, you can figure out kind of by elimination how many non-real roots you've got. In this case, we're thinking, okay, I've got 3 roots, but only one of them is real. So I must have 2 more, and they must be complex. Where are they? Hiding in this area where they would be real if only this thing were moved slightly downward. It's kind of tricky reasoning to follow when you're just working off a graph. If we had numbers, this would actually be a little easier, I think. But anyway, here's our curve. Let's move it out and see how it behaves. Okay. We could have this curve here, and it would have 2 real roots. We could have it here, and it would have 2 real roots. Or we could be here, but this section here where it flattens out is interesting. If we put that right on the axis, what kind of behavior is that when a curve comes down like it's thinking of turning away from the axis and then decides, no, I actually go through? This is what we call an inflection point, and this represents an odd number of roots, 5 or 7, something like that. I'll keep it simple and assume that there are 3 roots here. So we've got 1 real root, 3 real roots over here, or a root of multiplicity 3. So overall, this thing is 4th degree. It's 4th degree, which means a total of 4 roots. Some may be real and some may be complex, but overall the total should be 4 when we get to the end here. There we are. Total of 4. So the way they've drawn this curve, we have a real root in this position. We have 1 real root in this position. There must be 2 more roots someplace. We've only accounted for 2 real roots, and there aren't any others because it never touches the x-axis again. But in this area, where we had 3 roots before, there must still be 2 more, and they must be complex. to make our total of 4. So we had 3 roots in this area. When we moved the curve down, one of those roots drifted off to the left. He said, okay, well, I liked being real. I'm going to go back here and stay real. You guys want to be complex and stay in this neighborhood, that's fine. I'm going to shift to the left a little bit and remain real. So originally we had 3 real roots here. Now they've split up. One stayed real, the other 2 went complex. And our total is still 4 because this is a 4th degree equation. Third one. Actually, we'll do this. Okay, third equation goes, that's not a very good sketch. Let me try that again. Still not great, but it'll do the job. Okay, this curve, again, if I place this right here, you can see we get an inflection again. The curve flattens out like it's going to turn away, but then it goes, no, I will go through, and it continues on. So its curvature goes down and then back up. This means we have probably a root of multiplicity 3. It could be 5 or 7 or 9, or I'm going to keep this as simple as I can and just say there are 3 roots here. So in this position, this function has 3 real roots. However we move it up and down, it should always retain 3 real roots. Or, I'm sorry, 3 roots total. When we move it downward, what do we get? Well, now we only have 1 real root. Right there. The other 2 would have to stay in this area. It's the same situation as in example 2 living here. When they're downwards, one of these roots said, well, I'll be over here because I read somewhere I have to cross the x-axis at least once. I'll take care of that. The rest of you guys can stay here in this inflection because we still need to have a total of 3. So right there, our root. And in this region, our total has to be 2 more roots, and they will be complex. So just sliding the curve, maximum number of real roots. Here's a challenge. Now they're giving us then it drops sharply, turns around sharply, flattens out again, and climbs forever. If we move, let's have 2 here because it touches the axis and turns away, another one here, total of 3, and another one here, total of 4. Can we do any? Here's the wrong way to go. Here we only 2, 2, 2 of multiplicity 2, so our total's still 2, and now suddenly 0. We have no real root, so that was not an improvement. How about if we go the other way? 2 in different places. 2, 2, 2, 2, 2. Here we had 2, 3, 4. Here I think we can do even better. Here our total is, following the blue line, 1 real, another 1 real, total of 2, another real, total of 3, and we have an inflection on the x-axis which brings our total up to 6. To get this kind of S inflection, you have to have an odd number of roots other than 1. So right here, I think we can measure 6 roots. That tells us that this curve must be at least 6th degree. So if it must have at least 6 roots, how many are accounted for right now? We've got 2 here, and another 1 there. That brings our total up to 3. And that brings our total up to 4 real. This curve, as shown, has 4 real. The total's got to be 6, though. So there have places where complex roots are hiding. We have to have 2 more to bring our total up to 6. Where could those be? Well, remember this spot? This was an inflection. This used to have 3 roots hiding in it. One of them has now drifted left. He said, okay, I'll stay here on the x-axis. The rest of you can stay put. This is the most likely place that we would find another 2 roots to bring our total up to 6. So in general, with these, the kind of shape you're looking for is where the curve translated up or down would have either 2 or, in a case like this, a multiplicity 3. If you slide the curve up or down, generally what happens, these tests, is drifts off and the other 2 stay in place. You remember in our notes we said that non-real zeros always come in pairs. They're always called conjugate pairs. So when you find complex roots, you expect to find 2 of them, or 4 of them, or 6, some even number. And you can see in all of our examples, first example had 2 complex roots, 2. They're always showing up in pairs. If that's happening, that's a good sign that you're doing things right.